So we're going to pick one and just calculate the delta G. So we can look up these values of formation for our products and our reactants and plug them in, and we get a value for delta G naught of plus 79.89 kilojoules per mole. So we have a positive value here. So without doing any more math, which we'll do in a minute, do you expect a large or small value for K for the equilibrium constant if delta G naught is positive 79.89 kilojoules per mole? We would expect it to be small. And you probably already knew that there's a lot of H2O in a glass of water. So again, from that perspective, we'd also expect it to be small. So now we can plug those values in. We calculated this delta G. We know the gas constant. We're at room temperature. And so we get a value of K as 1.0 times 10 to the minus 14th at room temperature. And that's a small number. So the very small value indicates that only a small percentage of your H2O has ionized, and that mostly there's H2O in a glass of water, not so many ions. Not many of the molecules have ionized because K is a small number, not a lot of products at this equilibrium. So there's a lot of H2O in a glass of water. So this particular K has a special name, and it's KW, W for water. And this term and this number, if you haven't memorized it in high school, you probably will by the time you're done with problem sets. This is a very valuable number. You'll be using it a lot in calculating acid-base problems. And you will end up memorizing it whether you want to or not. So then Kw equals your hydronium ion concentration times your hydroxide ion concentration. Now for a minute, let's consider why that's true. So our reaction, it's products over reactants for an equilibrium constant, but I'm now, all of a sudden, I don't have my reactants going on in here. So the Kw is expressed in terms of the concentration of hydronium ions times the concentration of hydroxide, and it doesn't have this water term at the bottom. And that will be true for any problem in which the water is a solvent. And so you can, it's really not going to be changing very much. A solvent is nearly pure, and when you have a nearly pure solvent or solid, it's not included in the equilibrium expression. So we'll see other examples of this as we go along. So we always want to ask yourself, is this the solvent? If so, we're talking about very dilute things going on in solvent. The solvent concentration isn't changing very much, so it drops out of our term. So because Kw is an equilibrium constant, the products are always going to be equal to the same thing at the same temperature. So at room temperature, or 298 Kelvin, it's always going to be equal to 1.0 times 10 to the minus 14th, and that's why it's such a valuable number. And when we're talking about acid-base problems, you're almost always going to be at room temperature, just to not make life more complicated for you. So you can pretty much assume it should be in big, bold letters if the temperature is not room temperature, so that you can use these values.